Building software is a difficult task because it involves managing all the data and computation in a certain algorithm. Making it reliable is even more difficult, especially in the context of concurrent and distributed software, because one needs to manage two or more computations and needs to understand the communication and synchronization of these processes. In this scenario, it is even more important to have a tool to mechanically detect whether a program is correct or faulty. This is the area of software verification that studies if a program behaves as expected. Verifying reactive systems is even more difficult, for example, in the case of drones or in smart buildings, where systems need to interact with the physical environment. In this case, it is even more important to have a tool such as Runtime Verification that really helps in verifying this type of systems. So, for example, in the context of smart buildings, we can verify the fire risk system in such a building by placing a monitor in each of the rooms. These monitors will be equipped with CO2 and temperature sensors, and they will check the increments in both variables. Then, whenever they detect that these increments are higher than a safety threshold, they can raise a flag for the specific room. Combining the partial results of each of the rooms, they can output the final verdict for the whole building. So, using our contributions, we can improve the privacy, efficiency, and add fault tolerance to the distributed monitoring, which are key advantages over centralized solutions. There are three main objectives of this thesis. First, we define what is decentralized monitoring and distributed monitoring using rich verdicts. Then we provide algorithmic solutions and prove formally their correctness. And finally, we implement those solutions and verify them empirically with experiments. The main contribution of this thesis is a decentralized monitoring algorithm for synchronous networks using streams. Then we extend this work for more realistic network models such as time asynchronous networks. And on top of that, we add fault tolerance, allowing the monitors to be resilient against message loss and message duplication. The second contribution of this thesis is a translation between synchronous and asynchronous monitoring languages and their algorithms for the decentralized setting. First, we build a decentralized asynchronous algorithm, and then we extend a previously available translation for the decentralized setting. We find that we can still use this translation, but now it requires more computational resources. With this contribution, we have a clear understanding on when to choose one technique over the other based on the specific situation.